Alrighty, according to my time it's 2 o'clock, so we might make a start. Good approach to asphalt pavement design. This webinar is proudly brought to you by the National Asset Centre of Excellence, or NACO for short, in partnership with the ARB Group, TMR and APA. My name is Angela Ratz and I will moderate today's session and provide technical support if needed. My details will be on the next slide. Guys, if we can just tick that over, please.
Sorry, it's just frozen on us.
Oh no, it's frozen on us. That's all right. Not a worry. We'll get it working in just 1 second. Or in fact, I can pop the details up on my screen also. No, there we are. Okay, we're unfrozen. Well, sorry about that short delay there, ladies and gentlemen, but thank you for your patience. So as I was saying, my name is Angela Ratz and I will moderate today's session. If indeed you do require any technical assistance along the way, please do chat to me via the chat box and I'll be happy to assist you. Now let's run through a few housekeeping items before we kick off today. As always, we are recording today's session and it will be made available with all of you on conclusion of the webinar, together with the presentation material. Webinars do work best when they are interactive, so please don't be shy. We'd be delighted to address any questions along the way. Please type those into the questions box or into the chat at any stage of the presentation. Now, it's with great pleasure that I introduce our speakers for this two-part webinar, all of whom are joining us remotely from Queensland. Firstly, please welcome Peter Bryant of TMR. Peter has some 20 years engineering experience in private and public sectors, both in Australia and abroad. Peter is currently the Principal Pavement Design Engineer at TMR. Welcome, Peter. At the time of the work presented in this webinar, Eric Denneman was leading the ARB Pavement Technology and Asset Management team in Brisbane. He has since joined APA as Director of Technology and Leadership. Eric specialises in performance-based design and specification of asphalt materials and the development of design procedures for asphalt and concrete pavements. Hello, Eric.
Hello,
and finally, hello. And finally, please join me in welcoming Dr. Jeffrey Lee, a Principal Pavements Engineer from the Pavement Technology team at ARB Group. He has over 18 years of experience in the design and assessment of pavements for urban and rural highways, industrial and airfield environments. Thank you, all three of you, for your time and effort in preparing today's material. And I will now hand over officially to Peter to tell us a little bit more about what we can expect to learn in this webinar. Thank you, Peter.
Thanks, Angela, and welcome everyone to this webinar on a new approach to asphalt pavement design in Queensland. The purpose of this webinar is mainly to release a draft technical note which describes some fairly significant changes to the way that we will be designing asphalt pavements in Queensland in the future. And we'll be seeking stakeholder feedback on the draft technical note over the next few weeks. In the webinar, we'll also summarise some of the relevant background research behind the new procedures, and we also hope to facilitate an understanding of the content of the technical note, because a lot of the changes will be quite new to a lot of people. The agenda for the webinar, starting today, I'll give a brief introduction and overview of the proposed changes. Eric will then discuss the flexural modulus and fatigue aspects of the proposed changes. Then Jeffrey will finish part one with a discussion on the upper limit on design traffic. Then tomorrow we'll reconvene and I'll be doing a fair bit of the presenting then, covering an improved method for consideration of multiple axle loads. I'll also go through a pavement design example which brings together a lot of what myself, Eric and Jeffrey talk about, and also some details about implementation and how stakeholder feedback can be provided. A lot of the asphalt pavement design related research that's gone into the tech note has not just been done by the NACO projects, it's also been done through some Austroads and APA work. It's the NACO projects that are bringing you this webinar today, but we do talk about a lot of the content that's come from other projects as well. This research has shared common goals, which is mainly to reduce the cost of asphalt pavements and achieve better value for money, and generally improve the pavement design process to better match field performance. There's been a lot of linkages between these projects, as well as linkages with research internationally, such as in the US and Europe. The NACO projects have aimed to improve value for money and optimise asphalt pavement design in three main ways. Firstly, by addressing Queensland-specific issues, in particular the behaviour of asphalt at our warmer temperatures. Secondly, bringing together the outcomes of the various research projects into something that can be practically implemented. And lastly, accelerating the implementation of the research, as we are quite keen to see the benefits of the research used in practice. The NACO P10 and P39 projects, as well as covering their own unique parts of the overall asphalt pavement design puzzle, have done what none of the other projects have really set out to do, and that's bring all the relevant parts of these projects together into a single practical guide, which is targeted at pavement designers and asphalt producers.
Peter, where can we find these reports that you're pointing to here?
So the reports, all the Austroads reports that are listed there, well, they're the Austroads projects that are listed, but you'll be able to find the relevant reports from those projects on the Austroads website. And the NACO projects, there is a NACO website which you could find. I think there's links through the ARB website, and some of the reports, that's only a new website, but some of the reports are starting to get uploaded onto that website. So all the information can be found there. So today we'll go through the main content of the technical note today and tomorrow. It is meant to be a stakeholder consultation session. We're not necessarily chasing feedback today because there is quite a lot of information to take on board, but we'll be happy to take questions after each session, as Angela mentioned, and the feedback can come in the few weeks after this webinar. The proposed technical note can be summarised into four main changes compared to current pavement design procedures. These are changes relating to the asphalt design modulus and the asphalt fatigue relationship, an upper limit on design pavement design traffic for assessing asphalt fatigue, and a new approach for considering axle loads. As well as benefits in reducing pavement costs, the changes provide a more fundamental design approach with better links between asphalt mix design and pavement design. So the changes are very much suited to the introduction and assessment of innovations, in particular materials like EME2 asphalt or polymer modified binders in asphalt. And that's not easily achieved with the existing pavement design procedures. So just quickly looking at the first main change, which is defining the asphalt modulus through a flexural modulus master curve. Currently, presumptive moduli from indirect tensile testing or resilient modulus testing is most commonly used to determine pavement design moduli. The use of the presumptive design values will still be an option in the new method. However, the new method also includes the option to use a mix-specific modulus master curve rather than the presumptive values. And in a moment, I'll hand over to Eric and he'll cover that in detail. The second main change proposed is to allow the use of a mix-specific fatigue relationship, which would be done in conjunction with the mix-specific modulus. Use of the presumptive shell relationship that's currently used will still be an option, and Eric will also cover this change in detail and the background behind it. The third main change proposed is an upper limit on design traffic in full-depth asphalt pavements. In the current Austroads pavement design procedure, asphalt thickness increases indefinitely with increasing traffic. Various research undertaken more recently suggests that this is not necessary and not providing value for money. So in the technical note, asphalt thickness is capped, and that's done by an upper limit on design traffic. And Jeffrey will cover that aspect in detail. And the fourth and final main change in the technical note is a new approach to considering multiple axle group loads. In the current pavement design method, traffic loads are converted to standard axles, and pavement modelling is then based on the strains under a standard axle. In the improved method, the conversion to standard axles is not required, and strains will then be calculated under every axle in the traffic load distribution. I will explain that aspect in more detail in part 2 of the webinar tomorrow. So why do we actually want to make all these changes? In summary, we are implementing research that has identified improvements to pavement design methods, which has benefits in reducing costs and encouraging implementation of innovations by recognising their improved capabilities in the pavement design. This chart demonstrates the progression of typical full-depth asphalt pavement designs in southeast Queensland in recent years. On the vertical axis, that gives us the total asphalt thickness, and along the horizontal axis is the year of the design standard. For this example, this is a typical motorway in southeast Queensland. The design inputs are on the left-hand side there with 80,000 vehicles per day, 10% heavy vehicles, 4% growth, so ending up with over 150 million ESAs in 30 years. The pavement structure is also shown on the left-hand side. It's a full-depth asphalt pavement with an SMA surfacing and an AC14 intermediate course and an AC20 base course. For this example, in 2009, the asphalt thickness would have been 430 millimetres, which you can see from the chart. Around about 2012 or 2013, there was a lot of focus on asphalt thicknesses and a lot of concern that the asphalt thicknesses we were getting from the design procedures at the time were providing thicknesses that were greater than what they really needed to be for the intended pavement performance that we were expecting. So in 2013, we made some significant updates to our pavement design supplement, which were really targeted at reducing the thickness of asphalt pavements. So using the 2013 pavement design supplement, for this same design example, the thickness would have reduced, or the thickness reduced from 430 mils down to 370 mils for the same situation. This technical note that we're now releasing introduces further improvements to the design procedures based on more recent research, and it is expected to bring immediate benefits in justifying a further reduction in asphalt thickness, in this example down to about 345 millimetres, and that's using current asphalt mixes. The chart shows that further reductions should come by optimising asphalt mixes for fatigue performance, and the technical note is well set up for that to occur in the future. Just where we end up in terms of thickness, we don't really know. One thing we do need is a better link between field performance and performance in the lab in some of these tests that Eric will shortly be talking about. So I think that's really where we need to focus our attention in future research. That's just a brief overview of the changes to help you get your mind around what's coming up in the next presentations. We'll go into a lot more detail in the following presentations. But are there any initial questions at this point in
Great,
time?
thank you. Thank you so much, Peter. I will remind our audience that this is your opportunity to gain answers to your questions from our expert panel. So please don't be shy in submitting those questions along the way, and we'll address them as we go. We do have a question, Peter. I'm wondering if the new procedures will or can be used for current projects.
That's a very good question. I think for current projects, we just need to be mindful that the technical note is currently a draft, so there may be contractual issues that need to be thought through before it's used. I would suggest to pavement designers, I would certainly encourage them to think about using it, but the final approval to use the technical note in any project really needs to come from the relevant TMR project manager for the project. So pavement designers should be asking the question to those project managers. Possibly, or most likely those project managers will come to the TMR pavements branch to get some input, and we'd certainly be suggesting that they do consider using it. But they just need to get the final official okay for that to happen before they go and use it, especially while it's a draft document.
Great. Okay, a question has come through from Saeed, so I'll shoot that through to you, Peter. It reads, I'm just wondering what were the fundamental changes made to the 2013/2016 supplements which resulted in asphalt reduction in the provided example?
Yep, so the main changes that were made, so we were slightly constrained, I guess, by the Austroads Pavement Design Guide, where we didn't want to depart away from that. So we made a lot of changes that had really introduced some conservatism into the thickness design method. So we were designing for a 40-year design life, 97.5% reliability. We had conservative inputs for the foundation. So all those things we addressed. We also revisited the presumptive design moduli that we were using, and based on more recent mixes we're able to increase the moduli, which resulted directly in a reduction in thickness. So it wasn't really one individual thing, it was a whole lot of little things that really added up to the difference that you can see from that chart between the 2009 and 2013 thicknesses.
And there was a whole consultation process as part of that as well, as I understand.
Yeah, that's correct. So, yeah, there was a lot of input from industry and from also TMR districts about those changes at the time. So it wasn't just the Central Pavements Division making changes. There was a lot of input from a lot of different people across the industry.
Great. All right, thanks, guys. Now that question was from Saeed. Thank you very much for sending that through. Quick question here from Alan. Alan's asking if foamed bitumen in or out of scope, given is currently being modelled as asphalt. Maybe I should rephrase that. Is that making sense to you guys?
Yeah, no, I understand the question. I'd say at this stage that's out of scope, but that might be something Rama might like to follow up in the future. This research and the technical note are certainly targeted at asphalt.
Great, thank you, Alan. I might just shoot through one more question and then we'll move on to the next stage of the presentation. So both Graham and Brett are asking about the technical note. So will the technical note cover thin surface treatments, and when will the final version of the draft tech note be ready?
Yeah, so the technical note, the procedures in that can certainly be used within surfacings. And the second question there, at the moment we're releasing a draft, and I'll talk a little bit more about this tomorrow, but we'll be seeking feedback from stakeholders over the next month, and then there'll be another period to resolve any issues that are raised by stakeholders so that we can agree on the outcome. It's hard to predict just how long that might take. Ideally, we'd like to finish it by the end of the year or certainly early next year, but really that really just depends on what comments we get and what feedback we get.
All right, thank you very much for your questions, guys, and we might move on then to the next stage of the presentation, which I believe will be covered by Eric, and we'll be looking at flexural modulus. Goodness, I hope I've pronounced that correctly. And to everyone who's been great in submitting your questions, we've actually been inundated, so thank you very much. Keep them coming and we'll address them as we go. Thanks, Eric.
Thanks, Angela, and good afternoon, everyone. I've got a two-part presentation. I'll be talking about developing mix-specific flexural modulus master curves, and that will be followed by the procedures for developing mix-specific fatigue models. Now, this presentation is going to get slightly technical. Normally, I don't put equations in my presentations, but there was no escaping that this time. So before I lose too many people, I just wanted to get a couple of key messages across. I guess my main take-home messages from this would be that, first of all, that using this flexural modulus and the fatigue equations we're doing within the existing design framework that we're using for Ostrodes and the TMR supplement, so we're not going outside of the boundaries of that framework. And then the second message is that it may look like a lot of additional work that has to be done for these mixes, but you have to put that in context. So for some of the high performance mixes we're already doing quite a bit of testing, EME2 for instance, and this would really be only a limited amount of extra tests for these very specific high demand mixes that we're designing. So I guess those are my two messages, and with that I'll start my presentation. So I'll be running you through what we used to do, what we're doing right now, and what we will be doing. So what we used to do within the Ostrodes and the TMR supplement framework is run resilient modulus tests, like as shown on the left of this page. So we do a test at one temperature and one load frequency, and then we take that test performed at one single condition to predict the modulus of that mix at a whole range of temperatures and load frequencies as shown on the right. We're using the relationships that are shown on the right of this slide. So those are in Ostrodes. So basically what it means is that we're extrapolating the results from a single test, so a single data point, and we are predicting the resilient response of that material over a whole range of loading speeds and temperatures. Now, so that's the first thing that will be changing. We will be testing, we'll be starting doing 4-point bending flexural tests, so the 4-point bending tests shown on the right, and we'll be submitting asphalt specimens to tests at a range of frequencies and temperatures. So on the graph on the right shows you the results of such a test. So what you can see there is the markers indicates tests performed at 40 degrees C, 30 degrees C, 20 degrees C, 10 degrees C, and 0 degrees C. And at each of those temperatures, we perform tests over a range of frequencies, so a set of different frequencies. Then the next step is so that means that we have characterized the modulus of the material over a range of temperatures and frequencies. So that's quite a big departure from what we're doing at the moment. And then we're shifting those results to form a continuous curve, as is shown on this slide. So we're shifting the results of every temperature to form a single sigmoidal model by shifting the results in the frequency space. And we're doing that by using a temperature shift factor. I'll be talking about that a little bit later. And that way we can construct a master curve which can then be used to conveniently estimate the modulus of the material at any combination of temperature and load frequency. So why are we doing that? Well, first of all, so that will give us a convenient way of calculating flexural modulus at any combination of temperature and loading speed, but it also at the same time better represents the flexural modulus over a range of temperatures. So instead of assuming or taking a measurement at a single point and then assuming or estimating the performance of the material over a whole range of different temperatures and load frequencies, we're actually measuring it and characterizing the material over that range. And by doing that, we have a better representation of the flexural modulus over that range of temperature and frequencies. As a result, we're also going to get a higher modulus at elevated temperatures and low vehicle speeds compared to what we're currently doing under off-roads. And we get more realistic modulus values at low temperatures. And this slide is actually trying to show that this is a very important slide because this slide compares basically what we're doing currently under the TMR supplement to what we're proposing to doing with the flexural modulus. So these lines represent, and I'll take you through it. So the markers on this graph show you resilient modulus results for 3 different mixes. There's an EME2, there's an AC20 with REP, and there's a DG20 mix. So if you do a resilient modulus test, you're going to get 3 different resilient modulus values for those. And then the straight lines on this graph is actually how we predict the modulus at different frequencies using the current Ostrow's methods. So from that single point, we extrapolate over a range of frequencies using the Ostrow's method, and that results in a straight line on this graph. Whereas the actual measured stiffness using the flexural modulus test is represented by the dashed lines on this graph, and you'll see that's a slightly different, slightly different line or shape than what we assume under Ostrow's. And most importantly, on the left side of the graph, that is the high temperature, low load frequency space. We're getting higher moduli from the flexural modulus test than we're currently assuming under Ostrow's for all these mixes in point, and that's obviously a higher modulus at higher temperatures will lead to reduced pavement thicknesses. So that's a further benefit that we're getting out of doing this. Other reasons of why we're doing it is, well, these mix-specific master curves hopefully will open the doors to innovation because it allows people who do mix designs to get the full benefit of creating mixes that have higher modulus values, and especially if you combine that with higher fatigue values. So we're getting an actual competitive advantage of creating high performance mixes. In my opinion, we're also reducing risk at the same time because we're actually measuring the performance of these mixes over a range of temperature and load frequencies where we used to assume that. So this method should be more accurate and more precise in terms of characterizing the actual response of the material. And the final point in that is that we're now creating a much clearer link between laboratory testing and mix design. So, mix design and field performance. So this is really performance-based design that we're starting to introduce and creating a direct link between laboratory performance and what we're doing in the field. So if we then take a step back and look at why we can do this, the current Ostrow's Guide to Pavement Technology actually already uses the flexural modulus. It's always been the basis of the design method. It's just that we estimate the flexural modulus from resilient modulus values because in the past we haven't actually measured flexural modulus. Shell in 1978, which forms the Shell 1978 design method, which forms the basis for the current Ostrow's method when it comes to asphalt pavement design, also use flexural modulus. And the Shell nomographs that some of you may be very familiar with in terms of predicting or estimating the modulus of the material based on binder results is also actually used to estimate flexural modulus, and in a way represents a master curve. So for all these reasons, a recently completed Ostrow's study and the APR 51116, that's the final Ostrow's report to come out of that, actually recommended the reintroduction of the measured flexural modulus and the master curve as the basis for design. So that's basically what this work brings into the TMR tech note. Okay, then just a quick couple of slides on the test method itself. So we'll be using 4-point bending, and all that is you take an asphalt beam, you hold it on the ends, and you introduce a sinusoidal displacement load on the inner clamps and measure the load response of the sample while you're pushing up and down the inner clamps of the specimen. The test method that we'll be using for this is AGP T274, which replaces the older AGP T233 that you may be familiar with. So that is the older Ostro's fatigue test method. And changes with respect to determining the modulus between those methods includes the use of small strain. So the old method, and you could use it to determine flexural stiffness, actually was usually done at a high strain level. So for instance, 400 microstrain. The reality is that strain levels like that, when you're doing it as part of a fatigue test, you're already introducing damage to the sample, and you really should be testing for modulus in a space where you're not doing damage to the material. So that's why we moved to small strain. We'll be doing a temperature and frequency sweep. So the procedure for that is in the test method to determine the response of the material over a range of frequencies and temperatures. We'll be using a sinusoidal wave shape, so that is a departure from the Haversine wave shape in the T33. And there's the procedure to construct the complex modulus master curve. So the flexural modulus master curve is also in the test method. I'll be talking you through it, but don't despair if you don't get it immediately. The method is in the test method itself, and you just have to do it a couple of times for yourself to fully understand what is happening. This slide goes into a little bit of detail of what it is we're measuring, and I've included it because people may get confused on the difference between flexural stiffness and the complex modulus, or the E-star that you see pop up in papers here and there when people talk about fanciful things like master curves. The main difference is that the flexural stiffness is defined as the maximum stress over the maximum strain, whereas the complex modulus actually takes into account the time lag or the viscous behavior of the material. So when, and this is shown in the graph on the left, if we introduce a displacement load to a specimen, here shown as a strain, then there's a lag between the maximum strain and the maximum stress, and that lag is the phase angle, the time lag. So that's the viscous behavior caused by the viscous behavior of asphalt. If you have a purely elastic material, then the time lag or the phase angle is 0. If you've got a purely viscous material, then the time lag is, or the phase angle is 90 degrees. So if we then look at the representation on the right, that shows the relationship between E1, which is the elastic component, E2, which is the viscous or imaginary component, and E star, and then the phase angle is shown in that figure as well. So the calculation is very different from the flexural stiffness. However, the values will be quite similar. It's just that it's not exactly the same thing because we're taking the viscous behavior of the material into account. So that's just the background, and I thought it was important to include that. Then in terms of the test method, to develop a master curve, we want to do a temperature and frequency sweep over as wide a range as possible, just because we then get the best definition of our master curve. So you want to be doing testing over a range of temperatures, and the temperature shall not be more than 10 degrees apart. Also, the range of temperatures that you can actually physically do in your equipment will depend on the quality, if you like, of the thermostatic chamber, so your temperature cabinet. It's the same for frequency, so we want to do as wide a range of test frequencies as possible. However, pneumatic equipment is limited in terms of the frequency it can reach, so it all depends on, with your equipment, at what frequencies can you still get a proper and robust load signal into your sample. So pneumatic equipment is slightly more limited than hydraulic equipment in that respect. So if we then do the tests over a range of temperatures, we get a result table, something like this, and we need to test a minimum of 4 specimens. So what this result table shows that in the first column you see the temperature at which the test is performed, then in the second column the frequencies, and then we've got the results for every single specimen that you tested, and then we fit the master curve against the mean value that we get from this from the different specimens. Now you can also fit the master curve against all the all the single measurements. That's no problem. It's just that you're going to get the same result, so you may as well use the mean. I'm now going to talk you through the master curve construction in a couple of steps. So, like I said on the earlier slides, we run tests at different temperatures, as you can see here, and over different frequencies. So again, this is test results for 40, 30, 20 degrees, 10 degrees, and 0 degrees C. And then we shift those results in the frequency space to a single reference temperature, and in this case we chose 20 degrees C. You typically take a temperature that is in the middle of the temperature range that you tested over. I think the tech note actually requires you to shift it to 25 degrees C. Is that correct, Peter?
That's correct, yeah.
Okay, but that's really not important in terms of the result you're getting, as long as you do it consistently. So we're shifting those results, and we're doing that by fitting this sigmoidal model to the data. Now there are in literature a lot of different forms of master curves. You can use different functions to do this. We've chosen the sigmoidal model for the only reason that that is the model used by the US Mechanistic Empirical Design Guide and also the Californian design method. Like I said, there are other models available, but as long as they're robust, they should give you the same outcome. This is the model that will be used for the TMR tech note. So this is a bit of a full slide, but so at the top it shows you the sigmoidal model. Then like I said, we're shifting the results at every temperature in the frequency domain, and for that we need the temperature shift factor, so that to calculate a reduced frequency. So that's the second equation. So if we go back to the sigmoidal model, it's got the parameters in there are alpha, beta, gamma, and delta, which are basically fitting parameters. And then the only other parameter is FR, which is the reduced frequency. And FR is calculated by multiplying the frequency in the test, so that's F, by the shift factor as a function of temperature. And all that shift factor is really, that is the shift that is required to move those results that you see in the graph on the right to fit that function, that continuous S function. So for that we need the shift factor, and that is on the next slide. So the shift factor is this equation here. Let's get to that slide too. So that has got two fitting parameters, A and B, and as well as the reference temperature, and again for the purpose of this tech note that shall be 25 degrees C. So to get the shift factor you need to determine A and B, and to get the master curve you need to determine alpha, beta, gamma, and delta. And that we do in an Excel spreadsheet. So basically we solve both those equations, both the sigmoidal model and the temperature shift factor at the same time, and we compare in our spreadsheet the predicted modulus versus the measured modulus, and then it's basically a matter of changing the fitting parameters until you get the lowest error or the maximum coefficient of determination that you can do using Microsoft Excel Solver, and it really becomes an automated process once you've set up the spreadsheet. So it really is a basically an automated fitting function that's quite easily to fit to this data that you got from your temperature and frequency sweep testing in the laboratory. So I hope that's as clear as mud. But then once you are done, you can create these mix-specific master curves, and I've shown on this slide a number of these master curves and what they mean. So these are master curves for mixes that were actually tested as part of the TMR NACO P10 fatigue at elevated temperatures project. So we have here on this slide the results, the master curve for a GG20HM, an EME2, a DG14HS, so that is a polymer modified surfacing mix. Then there's an AC14M and another AC20 mix. And as you can see on this slide, the EME, so that's the green line, is the top line. EME has got a much higher modulus on the left part of the graph, and that is the graph where we have slow-moving loads like turtles and high temperatures. So there, EME has got the highest modulus. The lowest modulus is, as you would expect, the mix, the DG14 with the polymer modified binder. So this gives you, for these particular mixes, a very detailed view of the modulus at different temperatures and loading frequencies. And again, you can use this data to automatically calculate the modulus of the material at any temperature, any combination of temperature and load frequency. So that is if you have mix-specific information. If you do not have mix-specific data, you can still use master curves, and we actually propose that you do, because then we can have a consistent way of looking at modulus. So we've also introduced in the tech note, we converted the default values and the default correction factors for temperature and load frequencies from Ostrodes into a modulus master curve. So if you take those two equations from Ostrodes on the left, you can actually combine those into a single master curve, and the graph on the right shows you what happens then. So you get a straight line, and the cross indicates where your resilient modulus value would be in that. So it is possible to use the current Ostrodes values, default values, and turn them into a master curve. The only caveat on that is, of course, is that that approach will be as accurate, or lack the accuracy, if you like, that the current method in Ostrodes does. It's not exactly an improvement, it's just a more consistent use of master curves. And to get people used to using master curves. So the use of default values, the TMR supplement currently has a set of default values for asphalt. And they are shown for typical TMR asphalt mixes. They're shown in this table, and also shown in the tables is the default values for the master curves, to be able to use master curves with the current mixes using the default values that are already in the TMR design guide.
So Eric, will these default master curves, will that give the same answer as the current moduli in the pavement design supplement?
If I did my job correctly, they would, but we've checked it, Peter. I think that they will. Yes, yes, yes. Yeah. So basically, you get the same answer. It's just that you'll be using master curves. Anyone besides Peter have a question?
We've actually had lots of questions, Eric, so I might give you an opportunity to have a drink of water, because you're probably parched after all that content, and I'll start reading those through. So first questions come through from David, and David's asking, the master curve appears to asymptote high modulus but not low modulus. Is this because the master is based on binder properties and does not reflect the effect of the aggregate in the mix?
No. Well, the answer is actually that it does asymptote on both sides. The sigmoidal model is actually a symmetric model. That means the asymptote that's on one side is also on the other side. The thing the slide doesn't show is the current Ostrodes method, and also the current design, the current TMR supplement, limits the master curve at 1000 MPa. So that is what I did here as well. So if you look at the bottom left of this slide, you will see that at 1000 MPa that the line is drawn. That's because currently we minimize, well, the minimum modules that we use in mixed in pavement design for asphalt is 1000 MPa, and we're not proposing to change that. If you do testing in the laboratory, you will get values below 1000 MPa. I hope that answers the question. I don't know if Peter.
Yeah, no.
Yeah.
Sorry, Peter, did you have a comment you want?
Actually show that bottom asymptote as well. So we haven't cut off the 1000 MPa in that example. So when we send out the technical note, you'll be able to look at one of the figures in there just to see exactly what Eric's saying about the asymptote being symmetric at both ends.
Yeah, I guess to answer David's question a little bit further, the asymptote is typically between 200 and 500 MPa if you're doing laboratory testing. That's just that.
Alrighty, well thank you for answering that question, and thank you David for asking. And David did have another question. I'm just going to read these out in order of how they've come through, because there's certainly quite a few to get through. So David also wanted to know how is the flexural modulus determined for 20 millimetre mix when the beam dimensions are 3 times the max zone size?
There's currently the test method allowed those testing of those, and then not just in Australia, by the way. That's basically international. So the 20 millimeter stone size is not a limitation in terms of testing it on in the flexural beam test.
Okie dokie. Another question here from Stephen. Stephen was asking, bitumen properties change with time via the oxidation and aging process. How is this being accounted for when all testing is based on asphalt prepared from fresh pats? Has any consideration been given to testing asphalt taken from the field?
The answer to that, Angela, is that it isn't. It's a good question, but the reality is we are working within the framework of our current design method. Our current design method always uses fresh asphalt. And I'll get to that a little bit later when we're discussing the fatigue equations. But yes, we're within the framework of our current design method. The aging of asphalt materials is not taken into account in our design. That is no different under what we're doing here as it is under the current Ostro's and actually the original shell method as well.
Great, thank you. And thank you, Stephen, for submitting that question. One has come through from Brett, and Brett is asking, do we know how many labs in SEQ currently have the apparatus for this test?
This is something I'll be covering in a bit of detail tomorrow, but at the moment we're proposing for the testing to be done through independent labs, so that can be done either by TMR or a number of the major asphalt producers also have the equipment available. So there's certainly a number of options, and I don't think that'll be a detriment to implementing the procedures.
Great. All right. Now we've had a question here from David, and I'm going to apologise in advance if I'm mispronouncing any of these words. You'll have to bear with me. So David's saying, good to move the sinusoidal loading, the harvest line wave shape reverted to sinusoidal within about 10 cycles based on work by Bullen in the 1990s. Any comment on that?
Other than that's spot on, Angela. I was going to get to that a little bit.
Thank you.
And one part of that, and I'm just stealing my own thunder here, but one of the effects of that wasn't very well understood before is that actually not just does it revert to sinusoidal loading, also the strain level is half. As a result of that, is the actual effective strain level in the specimen is half of what you assume in the Haverstein test.
All right, thank you. Thank you, and thank you, David, for submitting that question. We might take one more question and then we'll move on to the next stage. Will that be okay with you, Eric?
Yep.
question here from George. So George is saying, historically, laboratory testing hasn't predicted field performance very well. Have you got long-term performance results which indicate that the proposed flexural modulus master curve will result in better prediction of field performance?
The answer to that question, Angela, is probably no. I'm not in no way proposing that this is better than our current method. It's just a better way of characterizing the modulus. So it's a better way of characterizing the material within the same method. Whether that is a better prediction of field performance, that is, well, in my opinion, is something that's separate. Yeah, it's no better or worse in terms of the lab to field performance prediction than our current method.
Great. All right, George, I hope we've been able to clarify that for you a little bit further. And we might move on with the presentation. Everyone who has sent through questions that we haven't addressed yet, thank you very much. We'll endeavour to get to those at the end of the presentation. So now we'll move on. Eric, I believe you're covering the next segment as well, mix-specific fatigue model.
Yes, thanks, Angela. So this part is slightly shorter than the previous part. So we'll now be talking about developing mix-specific fatigue models. So as the title says, we'll be developing fatigue models that can be used for individual asphalt mixes. So instead of using a general model that is valid for all asphalt mixes, we'll be using a mix-specific one. Okay, so this is again, I'm again going to take you about between what we're doing currently and what we propose to do going into the future. So what this slide shows is the current Osterode fatigue equation at the top, and most of you will be familiar with that. And basically what that says is that the fatigue, the number of cycles to fatigue failure in the field is a function of the volume of binder in your asphalt mix and the modulus or the stiffness of the material, so that's the E there, which basically means that you can take into account changes in temperature and load frequency as the E is a function of that, and the strain level at the bottom of the asphalt layer. Now that's the bottom equation here shows the Shell laboratory model. The Shell laboratory model is what the Osterode equation is based on. It's actually not even based on it. That part of the Osterode fatigue equation is the same as the original Shell laboratory models from the 1978. So that the latter part of the fatigue equation is basically a laboratory model from Osterode. So the Shell laboratory model, just to give you some background, was developed on 12 mixes from different countries based on testing that they did in the 1970s, and the Shell laboratory model basically gives you a prediction of the mean performance of those 12 mixes from the 1970s. Now that part of this, so that equation was put into the Osterode design method. So we're using the Shell laboratory model as shown on top, and then we multiply that mean performance of asphalt mixes in the laboratory by a laboratory to field reliability factor. So that RF there represents the shift of this laboratory performance to the field. And that is very important to understand, is that we're basically saying that the RF is a shift from the laboratory, for the laboratory model, to the field. And you could argue, based on what's on this slide, that we could replace the mean laboratory performance of 12 mixes testing in the 1970s with the mean laboratory performance of a current Australian mix tested now, and put in our own laboratory model there, as long as the testing that we're doing is similar, or the test configuration is similar to what Shell used to develop their general model for 12 mixes. So what we're proposing is to replace the Shell laboratory model with mix-specific laboratory models, which were determined in the exact same way, and then shift that laboratory performance to field performance using the same RF function that we have now. Okay, so that's what we will be doing, is run fatigue tests again on beam specimens in the laboratory and run those tests at different temperatures to develop a laboratory model um, that is fitted to all the data, so that the combined data at the different temperatures, and therefore the module or the fatigue performance again becomes a function of the modulus in the test and the strain level that was used in the test. So that's exactly the same as what Shell did in the 1970s, fitting a fatigue model against the data from those 12 mixes. We'll just be doing it to a single mix every time. So that's how you come up with a mix-specific fatigue relationship for mixes. And why would we want to go through all that effort? Well, first of all, we want to encourage the use and development of mixes with superior fatigue performance. And also I want to manage expectations a little bit. I don't want people to go run off to their laboratories tomorrow and start testing the mixes that we're currently using, because the likelihood that you'd be disappointed in the fatigue performance of those mixes is very high. Historically, asphalt mixes in Australia have not been optimized for fatigue performance, and therefore you can't expect these mixes to give a much better outcome than what Shell currently predicts. In fact, we have been finding the opposite, except for mixes like EME2 and mixes with polymer modified mud. So what we do, it is possible to develop mixes that have a much higher fatigue performance than the mixes we're currently using, and we want to encourage that for use within Queensland. And using those mix-specific fatigue models at the same time will open the doors to innovation, because when you're using mix-specific fatigue models in combination with mix-specific modulus functions or master curves, you can really get a competitive advantage if you're able to develop high-performance mixes, which is what we want to encourage. Because that will lead to reduced pavement thicknesses and will lead to more cost-effective pavements for the public. And at the same time, I would again argue that this is reducing risk, because instead of using this general model that was developed for 12 mixes in the 1970s overseas, and those mixes have very little in common with mixes currently used in Australia, we're actually testing the performance of mixes of modern Australian asphalt mixes. And again, we're creating here a direct link between laboratory mix design and field performance. So this is again this is a performance-related design method. Why we're doing it? So we're not going blind here. We have tested mixes for both modulus and fatigue here in Queensland, and the whole reason why this project was originally started is represented by the line shown on this slide. So what this graph here shows you, the required thickness of an asphalt pavement, and I can't remember the exact configuration, but it is an asphalt pavement designed for the same conditions, traffic conditions that is, for different places, so over different temperatures. So you can see here the continuous line shows you what the thickness that you would require for that asphalt pavement at different temperatures, and you'll see that you need a much thicker pavement in Queensland than you need in Ballarat or Melbourne. And the reason for that is that our current design method predicts that as the asphalt modulus goes down, because the temperature goes up, the deflections of the pavements increase, therefore the strains at the bottom of the pavement layer increase, and therefore the fatigue performance of the asphalt goes down. Now that is not actually what we would be expecting, because field data actually contradicts that, showing that at higher temperatures there is less fatigue damage. And that is a long story to get to what the mix-specific model shows. So when we start fitting these mix-specific fatigue equations, we can actually show that we don't see that effect, well, for this particular mix that is. So the dashed line shows you a design for a similar mix, but this time based on mix-specific modulus curves and mix-specific fatigue models, and you see that the temperature effect is for a large extent gone, and we can design pavements in Brisbane that are just as thick as you would use in Victoria for this mix. And obviously we don't know how far we can still optimize these fatigue mixes, because that's based on the current Australian mix. Okay, so just to take a step back again and to the argument. So why do we say that we can do this? The current design method of the Osterhout Guide to Pavement Technology uses the Shell 1978 laboratory model to characterize the fatigue performance of asphalt mixes. That is based on the mean performance of 12 mixes, and provided that we use suitable test condition, we can replace this laboratory model with a mix-specific laboratory model for a mix that we've actually measured. To allow that, and this goes back to that Haversine issue that David just raised, we need to replace the AGPT 233 with the AGPT 274. The difference between the two being is the 233 was based on an American test method where they use Haversine, which works perfectly well within their design system. But since Shell is a European design method, T274 is actually a European test method, based on a European test method. And the differences between the two is, so we'll be using sinusoidal wave shape, and as I alluded to earlier, that is because the Haversine load signal actually results in a sinusoidal load signal within the first couple of load repetitions of half the intended Haversine strain amplitude. So when you think you're testing at 400 microstrain, you're actually testing at 200 microstrain. That's what that means. So we need to shift to this new test method. We need to test 18 specimens per result according to the test method. So 18 specimens for a single fatigue result. And for use of this tech node, we'll actually be using slightly more specimens. I'll get to that. And there's also some changes to engineering properties like that complex modulus, also the dissipated energies in the test, etc., etc. But just for clarity, so we cannot use the outcomes, the historical outcomes of 233 for use with this tech node. You need to be testing according to 274. Okay, then just a couple of details on the test method again. So we'll be testing a minimum of 27 beams equally divided over 3 temperatures. We'll be testing therefore 9 beams per temperature at 10, 20 and 30 degrees C. A minimum of 3 strain levels per temperature, and all tests shall exceed 10,000 load cycles to failure. And 22% of the tests shall at least have 1,000,000 load cycles to failure. And obviously you have to tweak the strain levels to achieve that. And the test frequency will be the normal 10 Hertz that we're used to.
I'm just wondering, Eric, those 27 beams, I understand we have 5 beams for the modulus testing. Can those same beams be used for the fatigue testing, or is this another 27 beams?
Yes, there's nothing in the test method to stop you from using those same 5 beams. I wouldn't necessarily encourage you doing that, because I would be worried that you have imparted some damage on those specimens that you do through the modulus test. But the test method actually allows you to do that, because it's based on the European test, which also allows you to do that. So 7 beams and not 3 times 18 is that statistically we're fitting a model against we're fitting 27 beams or 27 results against a single model, whereas in the other test method we're fitting 18 results against a single model. So statistically we're very confident in the results. If we use 27, we don't necessarily have to test 3 times 18, because the slope of the line remains the same. And in terms of test results, they would look something like this. So you run the tests for different samples at different strain levels, and you get different results. There's a number of cycles to failure at different temperatures, and then that is the data set that you're going to fit your fatigue model to, and I'll just quickly run you through that. So that is the laboratory fatigue model that we'll be using. It's a 5-parameter model, whereas the model used by Shell is actually a 3-parameter model. And the reason why we picked this 5-parameter model is because it is more sensitive to changes in temperature. and that is very important in Queensland. So that's the reason why we went for the 5-parameter model. And again, we're predicting the number of load cycles to failure based on the modulus of the material and the strain level in the test, and then we've got 5 fitting parameters, that's C1 to C5, that we'd be fitting to the data. And we'll be doing that in much the same way as we did with the modulus faster curve. So we set up a spreadsheet in Excel, and we compare the predicted number of cycles to failure versus the measured number of cycles to failure, and we use Excel Solver to minimize the error between the two and maximize the coefficient of determination, and then you get a certain set for the best fit to data, and you get values for the C1 to C5 parameters as shown in the table at the bottom. Okay, so then we have developed our mix-specific laboratory fatigue model. So that's our mix-specific laboratory fatigue model, and we would have unique values for C1 to C5, and then we need to use that model to predict field performance. So basically what we're doing here is replace the shell general laboratory model with a mix-specific fatigue model, and to make the shift from laboratory to field, we use the same reliability factor as is currently in Ostro's. The only difference is that we have changed the laboratory performance from the general model to a mix-specific one. So that's it from me today.
Thank you, Eric. And once again, you seem to evoke lots of questions from the audience. So something about you, Eric. I am conscious of time, and obviously we don't want to take up any of Jeffrey's airtime either. So I might just send one question through to you, and then we'll move on and we'll see if we can take questions at the end. So questions come through from Graham, and he's asking, how are surface temperatures of above 40 degrees Celsius accommodated?
Currently the Ostro's method designs for temperatures at a depth of 100 millimeters. So that is what the, if we're talking about design temperatures of over 40 degrees C, I'm not aware of a place in Australia that would have design temperature of over 40 C. But even if you did, so we'll be testing at 10, 20, and 30 degrees C, and that is because of the limitations of the equipment. It's physically impossible to run a test at 40 degrees C, and we've demonstrated that. But because we run tests at different temperatures, and we've got different modulus values, and also you have to keep in mind that we have to not only account for different temperatures, we also, in terms of modulus, we also have to account for different loading speeds, because the test is run at a single frequency, and we actually have to extrapolate to other frequencies. So what we do is those 3 points, so we basically have, well, we have 27 test results, but the 3 stiffness points, and we put a graph through there. So based on 3 points, we create a function to predict basically to predict the fatigue performance at any of the points in between those. That's basically how I would explain it to people.
Yeah, no, yeah, I don't really have anything to add, but we are doing the modulus testing at 40 degrees. It's really just the fatigue testing that becomes unreliable at that higher temperature.
Yeah.
Thanks very much, guys. And, oh, sorry, Eric, go on.
But the general trend of the fatigue performance is very clear from running the tests at those 3 temperatures. I think that's the main answer to that question.
Great. Thank you, Graham, for engaging with us with that question. And now we might move on to welcome Dr. Jeffrey Lee to the microphone. And Jeffrey, you'll be talking about upper limit on design traffic. Is that right?
Yes, that's right. Thank you, Angela, and good afternoon, everyone. Just to clarify, we are discussing about putting an upper limit on design traffic in Queensland, and mainly this is for like a freeway type of situation. I would like to clarify that. And whenever we discuss about putting a cap on the current asphalt thickness, inevitably, the concept of fatigue engines limit comes to play. But to give you a bit more background, currently, asphalt thickness continues to increase with increasing traffic, and there's just a lot of studies nationally and overseas which suggest that really when the asphalt thickness goes to a certain point, keep on adding to it doesn't really bring us much benefit. So which is what drive this whole process of putting a limiting traffic onto our pavement design in Queensland. Well, from time to time you hear either the term fatigue entrance limit or entrance limit strain. To me, it is really describing the same thing. And in this slide, I've without going into full details on all these studies, just to give you some idea what research has been going on overseas and more so in Australia as well on this topic. The first two on the top one list are actually from the United States, and mainly they are laboratory testing to study the fatigue entrance limit of asphalt materials. And these studies they do consider modulus, rest periods, and asphalt healing, so on and so forth. So I think I'll leave it at that. And the third studies here is actually done by TRL at UK. In there, that they carry quite a comprehensive field observation studies, and their conclusion is that again to support the fact that when asphalt thickness goes beyond a certain limit, that there's really not too much benefit. And in Australia, there was a Road and the PMR project that was dated back in 2009. It was looking at the concept of the fatigue engines limit and and whether it was mature enough to be introduced into our design method at that stage. And I think the conclusion at that point was it wasn't ready at that time. And in more recent years, Australian Asphalt Pavement Association they have provided a methodology called Asphalt Pavement Solution for Life. It's quite a comprehensive studies, and I'll talk a bit more later on. And lastly, that there's a ongoing Road project TT2044, and one of the area that this project looks in is have a review of the current APA method, and also looking into what are the options that we can use to implement this fatigue entrance limit into the next off-road guide to pavement technologies. But at the bottom of the slide, I just want to emphasize that that there's still quite a lot of research done in this area, but like a full consensus among the different methods has not been arrived yet. But that doesn't mean that we can't be putting in an interim design limit on our pavement in Queensland. Since we are considering how to implement this in Australia, I'll just give a very quick overview of the two recent studies done in Australia. The first one is the APA method, and in this graph it shows one of the fatigue entrance limit that was proposed by the APA method. In simple terms, the fatigue entrance limit is a function of the asphalt modulus, and when we got a lower modulus, for example, at a hot summer in Queensland, we for that particular scenario, we were expecting a higher fatigue entrance limit, and the idea is that as long as the calculated strain, the calculated critical strain at the bottom of the asphalt stays within this fatigue entrance limit, then a very long pavement life is expected. That this study has actually taken into consideration a lot of the international studies, and and calibrated using Australian asphalt mixes, and has been using some Australian collected field data. So it's quite comprehensive studies. Just on this fatigue entrance limit in the Apple method, I think it's would be beneficial to point out that in the method it proposes considering doing checks on whether the strain is within the FDL for 3 different scenarios. First is the summer condition, and then the second one would be at the WMAPT, as Austro usually consider at this temperature, and the winter condition as well. But based on our studies, some observations that the winter FEL is never the dominating factor in terms of determining the asphalt thickness, and depending on a particular situation, either the summer or the WMAPT criteria will take control of the design thickness, and when the summer FEL is becoming the governing criteria, it's usually within 5 to 10 millimeter design thickness difference from the WMAPT. So from that, that's possibly reason for some simplification in this front. And then we move on to the next slide. Again, I did mention earlier in my part of the talk that there's an Austro project, TT2044, that's been ongoing, and very recently in June 2016, the project produced a discussion paper titled Asphalt Fatigue Entrance Limits Guide Implementation Options. So in short, right, basically the project gave a review of the international studies in this area, the Apple method, and more importantly, have presented 5 different options for, like, how can we be looking into implementing this in the next revision of the AGPT. In short, the first option A, B, and C makes specific reference to the fatigue entrance limit. Option D, which is like basically putting a limit on the design traffic loading. Option E is suggesting making modification to the fatigue relationship to allow for considering like the healing effect of asphalt at elevated temperature. For this technical note that we are proposing in Queensland, we're going to recommend adopting the option D, which basically is putting a limit on the design traffic, so that is what is going into the tech notes. So some reason why we are choosing this. First of all, some of these alternative methods, we believe that there's still further development that needs to be taking place before they can be implemented, and the fact that simply putting a limiting design traffic for Queensland is would be the most simple and compatible with the current AGPT method, with minimal change. Basically, we're putting an upper cap on the design traffic, and it can be implemented in short term while some of this research and ongoing discussion is taking place, and this is not just targeting purely on the perceived over design at high temperature zones in Australia. So I think that is quite appropriate at this point. This slide is just rather than giving talking in the space of design traffic limits, just put this limit. This is just a design example pavement profile I put up. You got the 50 millimeter AC 14 at the top, the AC 20 class 600 as the asphalt base, a 150 millimeter improved layering in the context of green sand. Usually that's like a lightly granular material and sitting directly on top of CBR 5, 7, and 12% subgrade. But one thing I think is has been the message across the different methods is that when we talk about having a pavement that is we expect it to have a very long life. We just can't ignore the fact that it needs to have a good foundation support, and for this reason, in the technical note, we're putting in the criteria to require some sort of improved layer plus any additional fill material, so that we can ensure that the top of the improved layer has at least 150 MPa, and so that there's a quite specific requirement we put down in there. So all these three different pavement profile, example profiles that I presented. This is a graph showing how the total asphalt thickness basically plateau and level off at 200 million ESO, and this limit is actually in line with the latest discussion in the Oslo TT2044, and which is considering that at the temperature zone between 26 to 34 degree, a upper cap of 200 million ESO is considered, and when I compare this with the upper pavement profile, from the method, actually the thicknesses are quite comparable, and that concludes my part of the presentations. Angela, any questions?
Thank you, Jeffrey. Thank you very much. We've had a lot of questions throughout, and I might just, before we get through to some of those at the end, given we've only got a couple of minutes left, it would be great to get some closing thoughts from each of you, and I guess a key message for our audience to take away or to have a think about, in fact, before tomorrow morning's session. Peter, would you like to go first?
Sure. Yeah, I think a key message, and maybe this hasn't come out so far yet today, but really we're commencing a journey, I guess, and this is really the first stage by making changes to our design systems which will allow us to link the mixed design and the pavement design together, which is something we haven't been able to do to any great extent in the past. So it is going to take some time to implement what's been talked about today, and I think we just need to keep that in mind. But we have to start the journey sometime, and I think all the work that's been done through the NACO program and the Austroads and APA projects, which has led to the technical note, has really set us up well for the design of asphalt pavements in the future.
Great, good message there. Eric, any closing remarks you'd like to make?
Well, Angela, I'm very much along the same line. So it's good to see all this work coming together and fitting together nicely. It's really there are big changes to the current design method, but at the same time we have all the ingredients to make it a success. I think it will be a long time before it reaches its full potential, but we do have mixes for which you can already start using this. I was saying this morning that the main thing you could do is optimize your EME2 designs to fit within this current design framework and really get the full potential out of using those mixes, because they really provide a higher modulus and a longer fatigue life. And we can already design pavements with it within the current Oslo design framework, but this gives you an extra edge in terms of optimizing getting the full benefit out of developing these high performance mixes.
Most certainly. Thank you, Eric. And how about you, Jeffrey? Any last words?
The upper limit that I presented, I guess it's just one aspect of the improvements that we propose in this techno. In tomorrow's section, actually, everything will be put together. So to realize, what's the combined effect of all these changes to the asphalt pavement thickness. So stay tuned and make sure you come back tomorrow morning for the second part.
Yes, we do hope everyone joins us tomorrow morning at 9 o'clock on the dot. Gentlemen, sorry, Eric.
While we're on plugs, I would also like to say that we have a paper into the ARC conference that has a lot of the, it has all the data of fatigue performance of some mixes we tested so far in it. So I think that is also something to look out for in this space.
Great, absolutely. Keep an eye out for that. Okay, there have been a lot of questions, and we're obviously not going to be able to address all of them, but one of the questions that has come through here is relating to, I guess, other state road authorities around Australia, perhaps New Zealand, and what's been their response to these changes? Is this something that might be adopted outside of Queensland?
Shall I respond to that, if you like? This is the first time we're telling them about it, Anton. No, so parts of it, there are different parts to this tech note. So the things, mix-specific, modulus, or the flexural modulus master curves is actually something that occurs in a recent Austroads report and has been recommended for implementation under Austroads. So I assume that other road agencies may well follow suit in implementing that. Some of the other things are new. We're talking about it for the first time today. I would say that part of it you'll probably see in design methods by other road agencies, and other parts you won't.
Yeah, no, I think that's a fair comment, and certainly there's a project to update the current Australia's pavement design guide at the moment, and there's certainly conversations within the state road agencies about some of these things that we've talked about. So decisions will be made in the next 6 months or so about some of these things, and they may or may not turn up in the Austroads guide.
All right, we'll keep an eye on the Austroads guides and whether they may or may not turn up. More news to follow. We might just finish off on this question that we received from Jonathan a little bit earlier, and Jonathan's asking, is any work being done on the relationship between fatigue damage and the observation of fatigue distress? How does a 50% reduction in flexural stiffness measured in the laboratory relate to in-service performance?
Well, again, Angela, this is where we refer back to the original Shell method. So Shell had shift factors, so that reliability factor in the Austroads, the short answer is the reliability factor in the Austroads design method is supposed to account for that, because that was already part of the Shell method as well. So that's part of why you need a shift factor from laboratory to field.
Does anyone else have any thoughts on that?
Yeah, I think the next stage in the research from a wider level really does need to look at that issue. We'd really love to have an accelerated load facility that might help with that, or undertake some trials in the field that can really compare the field performance against the laboratory properties. So I think that's something we'd really love to do in the future.
Fantastic. All right, stay tuned. Now, ladies and gentlemen, please don't forget, tomorrow morning at 9 o'clock Australian Eastern Standard Time, we'll be commencing part 2 of this particular webinar. So please do join us nice and early, bright and early at 9 o'clock tomorrow morning. As this webinar does shut down, you will receive a pop-up box on your screen, and that's your opportunity to give us a little bit of feedback on how we travelled today. Perhaps what you'd like to see more of, any feedback that you may have in relation to the webinars, please do let us know, as we do take the feedback very seriously. Thank you so much for joining us today. To the ladies and gentlemen of the audience, we hope you found it very useful. and we'll see you back again tomorrow morning. To our presenters today, Eric, Peter and Jeffrey, thank you so much for your time in preparing the material and presenting it. It's been very insightful. And for anyone who submitted questions that unfortunately we couldn't address, if they are burning, please don't hesitate to get in touch with our presenters. I'm sure they'd be more than happy to discuss them with you further. The recording of this presentation and the material, once again, as I mentioned earlier, will be available on the NACO website, and I'll be sending out an email to each and every one of you with those details. So thank you once again, and we'll see you bright and early tomorrow morning.